Okay, before we get to the second derivative test, let's revisit the key concept of first derivative test. So let's say we look at the neighborhood of x equals to 2, that f of x, the original, is going uphill and then flat and then downhill. Okay, so in this case, f of 2 is a local maximum. On the other hand, if in this case you go from a negative slope through 0 at this point to a positive slope, okay, that means that the original function f of x goes down and 0 and then goes back up, and so f of 2 is a local minimum. Now if you look at the f prime of x, the first derivative in this neighborhood, you go from positive, you're going up, slowly decrease it in slope, get to 0, and then goes down for the slope. That is the first derivative, which means that at x equals to 2, the slope, the first derivative, is decreasing. So in this case, we look at the slope of the slope, okay? That is the second derivative. So put it this way. The slope here, say at x equals to -6, the slope of the tangent would be like this, okay? This slope would be, say, 2, okay? And because it's all symmetric on here, this would be -2 for the slope, okay? And now when you get to x equals to -4, it's still increasing, okay? But the slope is smaller, right? So this would be 0.5, and here, because it's all symmetric, this would be -0.5, and of course when x equals to -2, the slope will be 0, right? So if you look at this, you see a constant decreasing of the slope, right? Which means that in this neighborhood, f double prime of -2, okay, because it's a slope of the slope, and particularly when x equals to -2, its second derivative, that is less than 0, okay? And so f of -2 is a local maximum, and so the local maximum when the slope goes down and the slope of the slope at that particular point is less than 0. So on the other hand, if you have a valley like this, okay, if you look at the slope of the tangent line, okay, so you go from a steeper slope going down, that is negative, say -2, and on this side it's +2. This one still going down, but it's less steeper, and so let's say -0.5. This would be +0.5, and of course this one is a flat one. So as you can see, the slope, that is the first derivative, keeps going up, and so the slope of the slope must be positive, okay? And so at this point, f of -2 is a local minimum. So a local minimum when your second derivative at that particular point is greater than 0, because the slope is going up. The slope of slope tells us something. So let's take a look at this very quick example. Find the local extrema of this function by using the second derivative test, okay? So first of all, of course, we take the first derivative. After factorizing it, I then set it to 0. So far, all we're doing is exactly the same as our previous example when we used the first derivative test. Now here's where the second derivative test kicks in. So you take the second derivative test by differentiating the first derivative, and then you put in these two numbers. So f double prime of -2 is less than 0. And because it's less than 0, you know that f of x has a local maximum when x equals to -2. Now you want to find where exactly that local maximum is, right? By using the original function. And so f of -2 equals to 103, and the local maximum is 103. On the other hand, if we look at the other x, so again, you put the 1 back into the second derivative here. It's 90 greater than 0, and therefore f of x got its local minimum at x equals to 1. And again, you put them back into the original function to know where the position is, which is -32, and so the minimum of the function is -32. Now here's a side note for you, very importantly. If the second derivative for that particular x also equals to 0, then the second derivative test doesn't work, and you must go back to use the first derivative test. And here's a note for you: if your first d is so difficult to differentiate, then you use the first derivative test, okay? And you just need to check the signs, whether it goes from positive to 0 to negative or vice versa. And on the other hand, if the first d is easy to differentiate, then of course you take the second derivative test because it saves you a lot of time. And sometimes in first d test, you come across with this kind of scenario. When you look at the slope, it goes from negative through 0 but goes back to negative, or positive, 0, positive. Then your curve would be something that looks like that, okay? And so you just need to say at this point x equals to -2 is not a turning point, so you can't say whether it's a minimum or maximum. And if you see this case, it keeps going down, and this one 0 goes back up. In this case, you can conclude by looking at the slopes, you can conclude that at x equals to 1, it's a minimum point. You don't even say it's a local minimum point anymore, because as you can conclude, it's the lowest point for the entire curve.